Hello. This lecture is on the Space Shuttle Challenger episode. The Challenger is now a classic case in engineering ethics, but it's important to us in two respects. First, it suggests important things about the relationship between the professions and management, or professionals who work within organizations and management. This includes engineers, of course, but it also includes nurses, actuaries, and the other professions that are represented at MSOE. So that's the first thing. The second is that it's really the Challenger that provides the motivation for the inclusion of the activity of moral friendship in professional life, as I see it, and I will argue for that toward the end here. So our discussion is it has three parts. First, we're going to take what's the narrative of the events. This is, if you're in HU 432, is in our text. If you're in HU 332, there is a link to this material on Blackboard. It is essentially the same material. So we'll look at the sequence of events for just a few minutes, and then we'll turn to the really important study by the sociologist Diane Vaughan, called The Challenger Launch Decision, Risky Technology, Culture, and Deviance at NASA. That'll be the main part of the lecture. And at the end, we'll summarize things and look a little more closely at the relationship between engineers and management in the Challenger. And then at the very end, again, discuss the motivation for moral friendship that the Challenger provides. The PowerPoint slides, let's see, the first 9 are basically data supporting material for the discussion. The remaining, beginning with slide 9, we'll discuss that toward the end, after we do Vaughan. So this, what we have in our book, and the link to online ethics discussion, is what Roger Beaujolais is really the central figure in this. Beaujolais was a senior engineer at Morton Thiokol. He had spent a good part of his career elsewhere, came to Morton Thiokol after the sealing function had been designed largely. So he had a little less in the way of ownership of it than others did. At the website, not in the text, but at the online ethics, in their section on the Challenger, if you get to the website, I've given HU 332 students exactly the link to that section. But for the rest of you, if you go there and just put Challenger in the search window, it'll bring up this material. And there includes an organizational chart, which is useful in locating some of the figures. In particular, the relationship between Beaujolais and Robert Lund. Robert Lund was the vice president of engineering. He's the figure who famously was asked to take off his management hat and put on his, or rather take off his engineering hat and put on his management hat as the vice president of engineering. He was a senior management figure who was the closest to the engineering function. Beaujolais said that he and Lund really didn't get along all that well. They're two very different personalities. Lund was a company man. He spent his entire career at Morton Thiokol, pretty much. Beaujolais came there rather late. Beaujolais was an engineer. He wasn't interested in management, and Lund was approximately the same age. That was an interesting dynamic. Let's start then. The chronology begins almost exactly a year before the launch of the Challenger. This is January of 1985. Thiokol would send down engineers after every launch to examine the solid rocket boosters that were retrieved from the ocean that were dropped, landed there by a parachute. Incidentally, that had turned out to be the main concern of Thiokol as the manufacturers of the solid rocket boosters for the preceding year. How do you recover these things? That wasn't always successful. Sometimes they sank. But every time that they were recovered and returned to Cape Kennedy, a thiokol engineer would examine the solid rocket boosters and particularly the O-rings. And in here, Beaujolais said, unfortunately, they didn't always send the same people. So they don't have, their experience base didn't have continuity. Beaujolais went this time in January of 85 for Flight 51C. Said during this inspection, he found evidence that hot combustion gases had compromised the primary seals on two field joints. That was the joint around the entire solid rocket booster. My concern heightened as a result of the large amount of blackened grease I observed between the two seals. Subsequent to reporting the findings to my superiors, I was asked to proceed to the Marshall Space Flight Center in Huntsville, Alabama, to brief them with a preliminary view graph presentation, which included my observations and an explanation of the scenarios that caused the seal erosion and hot gas blowby. Thiokol was then asked to prepare a detailed presentation as part of the flight readiness review for Flight 51E, which was scheduled for launch in April of 85. Flight readiness reviews were something of had the format of an adversarial meeting between NASA and their contractors. They occurred at three different levels. The bottom level was the least senior. There, the goal is to work out problems before they need to go to the next level and the next level of management. So both sides, both NASA project management and contractor project management, have the same interests in working out problems before the next level flight readiness review. So at this one, he says, yes, the presentation was given in February at three successively higher level review boards with refinements and contents made at each level. He presented his belief that lower than usual launch temperatures was responsible for such a large witness of hot gas blowby. But NASA management insisted that this position be softened for the final review board. Then he gives his conclusions. Now, at the website, there is something of an interactive sequence through the narrative. You have an opportunity occasionally to you're asked a question, then you click on it, you're given several options, do more testing, go to your superior, go to somebody else, and so on. I think this is the first one. So what's happening here is that NASA is asking Beaujolais, the contractor's engineer, to soften his judgment, to pull his punches, as it were. Now, that is to say, he said that his position be softened for the final review board. In other words, don't make it sound as serious as you're saying here. Yeah, that's useful to consider. Are there good reasons for complying with NASA here? You could think so. The manned flight is not for another year away. Certainly, you would think that there'd be enough time to work out any problems. You want to be cooperative, of course, with NASA. And in fact, he did. He did sign off with conditions acceptable. The next flight, our field joints are acceptable for flight. All right, but he's concerned, as is his colleague Arnie Thompson. If you look at the organizational chart, Beaujolais and Thompson are at the same level. Beaujolais is a staff engineer. Thompson is a manager. Manager is somebody who has at least one subordinate. And he and Arnie Thompson discussed the blow-by scenario and the effect of cold temperature on O-ring resiliency, which is the ability of the seal to restore itself to a round shape when the squeeze on the seal is removed. Arnie proposed that subscale lab tests be conducted, which would provide us with assessment data. The resiliency testing was performed in March and showed that low temperature was a problem. The results indicated that the seals would lift off their sealing surfaces for several seconds at 75 degrees Fahrenheit and in excess of 10 minutes at 50 degrees Fahrenheit. The data was discussed with Morton Thiokol Engineering Management, but was thought to be too sensitive by them to release. Now, 50 degrees, that's significant, because the lowest actual launch temperature in the database was 53 degrees. 50 degrees at subscale on a testing bed the seals would lift off their sealing surfaces for 10 minutes at 50 degrees. There was some controversy about this because the test was done in a horizontal position. Of course, in a vertical position, it was thought that the weight of the solid rocket booster would certainly contribute and be responsible ultimately for the sealing function. All right, so we have another post-flight inspection in June of '85 in this time in Utah. This time a nozzle joint, not a field joint, not around the whole circumference of the solid rocket booster, but a nozzle joint from Flight 51B, which flew in April of '85, was found to have a primary seal eroded in 3 places over 1.3 length up to a maximum depth of 0.120 inches. And the secondary seal in the same joint eroded 0.032 inches. It was postulated that the primary seal had never sealed during the full 2 minutes of flight. And again, there's thought that yes, but the secondary seal will hold because of the tremendous weight of the solid rocket booster. My former concerns now escalated because if this same scenario happened in a field joint, secondary seal could also be compromised, especially during a low temperature launch. So we have another flight readiness review. Presentation was given at NASA, to NASA at Marshall in Alabama on July 1st of '85, with an additional presentation on the overall status of the booster seal given the next day. Everyone, it says at the end of this paragraph, on the program for the first time was now aware of the influence of low temperature on joint seals. His concern is increased because of the lack of attention the problem is getting. At the website, among the materials are memos, separate memos that he and Thompson wrote to different people. Beaujolais wrote his to his immediate superior, but it gets transmitted then upward, up to certainly Robert Lund. So he says, an attempt to form the team was made on 19 July of '85. This attempt virtually failed and resulted in my writing a particular memo. The memo finally got some response and a team was formed officially. The first meeting was held on August 15th. The memo referred to is the one I read to the Presidential Commission. So everyone knows he is sent to an SAE conference to get some input from other people, but told not to tell anyone how serious the problem really was. This was not terribly useful. He says this task force was frustrated from the very beginning by lack of resources. And he writes a series of very damning activity reports, he says, in which I left no room for error about how I felt concerning the lack of management support. However, he never received any comments back and never knew if they had been incorporated into reports up through the management structure. I won't read it here, but it's useful to see what the contents of that memo were. He didn't mince words. He says at the end that if we do not fix this problem, it could mean catastrophic failure. You could lose the shuttle and its crew, and maybe even the launch facility if it blew up on the ground. All right, now we come to so now it's a year after when this whole narrative begins. It's now January of '86, the night before the launch. So allow me to read this. It's really dramatic. What happened was a NASA manager recalled, he was looking at the projected launch temperature, which is extremely low. And he had recalled that in the past, Thiokol had been concerned about low temperatures. In the intervening year, the process, which we'll get into when we get to Vaughn, was such that they had signed off on the seals. They had been given a waiver. Now, a waiver does not mean that somebody just says, we'll take it as it is. No, it's a waiver is much more involved than that, but does mean that it's seen as an acceptable risk. That's the most important thing. So the NASA management calls Thiokol, mentions the problem, and Thiokol engineers get on it right away. This is very early in the day preceding launch day. And they spent the day putting together the data that they have and putting it in view graphs and tables and charts. You've got to remember, this is 1986. There was no Skype yet, no Zoom, no internet. So all they had was teleconference and faxing documents. Major activity of the day focused upon the predicted 18 degrees Fahrenheit overnight temperature and meeting with engineering management to persuade them not to launch. The day concluded with the hurried preparation of 14 view graphs which detailed our concerns about launching at such a low temperature. The teleconference with Kennedy and Marshall started with a history of O-ring damage and field joints. Data was presented showing a major concern with seal resiliency and the change to the sealing timing function and the criticality of this on the ability to seal. I was asked several times during my portion of the presentation to quantify my concerns, but I said I could not, since the only data I had was what I'd already presented, and that I'd been trying to get more data since last October. At this comment, the general manager of Morton Thiokol gave me a scolding look as if to say, "Why are you telling that to them?" The presentation ended with a recommendation not to launch below 53 degrees, which was the lowest temperature, launch temperature in the database, which was not well received by NASA. That is understandable. That one of the PowerPoint slides, the first one really, after the title, was relevant temperatures. So 53 degrees is the lowest temperature under which they launched. 29 degrees, I believe, I don't have it in front of me here, is the anticipated launch temperature. And something like 31 degrees was the temperature in the specifications under which it should have been safe to fly. So it's no wonder that NASA is disappointed, to put it mildly, that they're supposed to work down to some temperature much lower than 53 degrees, something like 20 degrees anyway, lower than 53. And here they are recommending that you do not launch below 53 degrees. The Vice President of Space Booster Programs at Thiokol, Joe Kilminster, was asked by NASA for his launch decision. He said he did not recommend launching based upon the engineering position just presented. Then Larry Malloy of NASA, who was at Kennedy, asked George Hardy. Malloy is the project, is the senior NASA person at the teleconference, or certainly at Cape Kennedy. Malloy was asked he was at Kennedy, asked Hardy, who was at Marshall, for his launch decision. George responded that he was appalled at Thiokol's recommendation, but said he would not launch over the contractor's objection. Now, everyone respected George Hardy very highly, so for him to have said that he was appalled carried a lot of weight for everybody involved. Malloy spent some time giving his interpretation of the data, with his conclusion that the data presented was inconclusive. Now, this is going to be very significant later. Just as he finished his conclusion, Kilminster asked for a 5-minute offline caucus to reevaluate the data. And as soon as the mute button was pushed, our general manager, Jerry Mason, said in a soft voice, "We have to make a management decision." I became furious when I heard this because I knew that an attempt would be made by management to reverse our recommendation not to launch. Some discussion had started between the managers when Thompson moved from his position down the table to a position in front of the managers and once again tried to explain our position by sketching the joint and discussing the problem with seals at low temperature. Arnie stopped when he saw the unfriendly look in Mason's eyes and also realized that no one was listening to him. I then grabbed the photographic evidence showing the hot gas blow-by and placed it on the table and, somewhat angered, admonished them to look and not ignore what the photos were telling us, namely that low temperatures indeed caused more hot gas blow-by in the joints. I, too, received the same cold stares as Arnie, with looks as if to say, "Go away and don't bother us with the facts." At that moment, I felt totally helpless, and that further argument was fruitless, so I, too, stopped pressing my case. Now, Beaujolais at his presentations, one of which was at Marquette in 2003. We took students from MSOE over to hear him. He said that he was told later on that he and Thompson were actually screaming at Mason and other managers at this point. This is important because in the teleconference, the actual teleconference, not many engineers spoke. We'll consider that. We can explain it. It's largely the fact that there was very little data to go on, and that, of course, engineers work on the basis of data. There wasn't much. But here, they were adamant that the launch ought not to proceed. So this is what followed, made me both sad and angry. The managers were struggling to make a pro-launch list of supporting data, but unfortunately for them, the data actually supported a decision not to launch. That list of reasons for launching is in slide 8, and then the next slide is Beaujolais' critique of the reasons that Joe Kilminster gave for Thiokol's then recommending launch. During the closed managers discussion, Jerry Mason asked him in a low voice if he was the only one who wanted to fly. The discussion continued, then Mason turned to Bob Lund, the vice president of engineering, and told him to take off his engineering hat and put on his management hat. The decision to launch resulted from the yes vote of only the 4 senior executives, since the rest of us were excluded from both the final decision and the vote poll. This is the management decision. The telecon resumed, and Joe Kilminster read the launch support rationale from a handwritten list and recommended that the launch proceed. NASA promptly accepted the recommendation to launch without any probing discussion and asked Joe to send a signed copy of the chart. Now, as far as the relationship of engineering to management, we have to bear in mind that everybody here was an engineer. All the managers were engineers too. But this idea of switching hats indicates that there's a difference in points of view, in values, really. That's there's more in his narrative here, but that's this is so they recommend launch, and of course, the disaster follows. Let's turn next to Diane Vaughn's very important ethnographic study. She interviewed both NASA and Thiokol personnel for thousands of hours in arriving at this. Vaughn says, through the end of 1985, the solid rocket booster work group had consistently defined the solid rocket booster joints as an acceptable risk. This is the belief in the redundancy of the joint, supported by a scientific paradigm that we'll get to in a moment, was instituted prior to 1986. The redundancy and the scientific paradigm behind it were crucial components of the worldview that many decision makers brought to the teleconference on the eve of the launch. Understanding the launch decision rests on knowing this important fact. Okay, so what is this all about? Somebody, I forget the man's first name, Vic, writes of what this scientific paradigm was and how important it was, particularly to those working at Marshall in Alabama. Vic writes, numerical probability methods developed by the Germans beginning with the V1 program during World War II followed into the American space program and were standard in the Mercury and Gemini programs. Of course, this was the government brought Fender von Braun, the great, actually was a rocket scientist, over to contribute to the Apollo program in particular. I guess he was here earlier for the other projects too. Now, during the Apollo program, however, so numerical probability was standard in the Mercury and Gemini programs. During the Apollo program, however, probability estimates of 1 in 20 of success in getting a man on the moon and back led NASA, for largely political reasons, to abandon numerical probability in favor of a qualitative or qualitative non-numerical methods. And there were two methods in particular: failure modes and effects analysis on the one hand, and hazard analysis. Failure modes and effect analysis was to identify hardware items critical to the performance and safety of the shuttle. In particular, those not meeting mission requirements. NASA applies this as follows. So here's the procedure. Define the system and its performance requirements, specify the assumptions and conditions to be applied in the failure modes analysis, develop reliability block diagrams or simple representations of system component interactions and dependencies, devise a failure modes worksheet and complete it for every identified failure mode, identifying worst case effects. Fifth, recommend and evaluate corrective action, including design improvements or redesign. The upshot of the failure mode process was to identify those components not meeting certain design, operational, or fail-safe requirements. From those, a critical items list was constructed. Then, hazard analysis, the other method, was this: using the failure modes and associated information identified from the failure mode analysis. The hazard analysis developed accident scenarios, essentially working backwards to the critical components that might participate in these scenarios. Hazard analysis also ranked critical items according to their failure consequences. The scheme accounted for the consequences of failure, but not their likelihood. This is the non-numerical part. These results were used by NASA in what it called its acceptable risk process. This was essentially a formal sign-off procedure meant to do two things. First, to ensure that the critical items not meeting fail-safe requirements received extra attention, in essence, a diagnostic function. And second, to communicate this with the organization so that everyone would be fully apprised of the implications. Before the shuttle could fly, critical items had to be subjected to design modifications or corrective actions to meet redundancy requirements. If corrective actions weren't feasible, a waiver request had to be submitted to NASA management that specified a rationale for retention, that is, a technical justification for retaining the critical item in the design. This might invoke such things as testing, inspection, operational experience, or measures to reduce failure potential. If the waiver was approved, the item was termed an acceptable risk. All right, so the waiver process resulted in something being having to be argued and shown to be an acceptable risk. The important thing here is that the acceptable risk process required justifying why a critical item should remain as a part of the design, with a presumptive remedy of redesign. At this stage, the burden of proof lay with the design, but this would later change in the case of the solid rocket booster field joints and the O-rings they contained. In 1984, Flight STS, that's Space Transportation System, 41B, that's the shuttle, sustained O-ring erosion that Vaughn argues fundamentally changed the engineer's perception of risk. For Flight 41B, pressure testing of the O-rings was increased from 100 to 200 psi in the interest of better assuring the seating. The root cause of the O-ring damage, the pressure testing itself, was now thought to be understood. The accepted risk it entailed now involved a trade-off of increased O-ring erosion for assured O-ring seating. From then on, O-ring erosion was no longer considered anomalous, but an expected condition within the operational performance parameters. It became taken for granted because it now could be causally explained and even rationalized as necessary. Thus, it came as no surprise when erosion again occurred for Flight 41C in April of '84. O-ring erosion had become a predicted and hence normal aspect of joint performance and a risk to be routinely accepted on missions. This is what Diane Vaughn later will term the normalization of deviance. Thought Call engineers had data on resiliency and data on redundancy, but no data on how resiliency affected redundancy. Thus, there was no temperature launch commit criteria for the solid rocket boosters. Vaughn resituates the events the night before the launch in a much richer ethnographic account than is represented by the standard version that we get, say, in the Rogers Commission report. The culture, as she says, the culture of production and structural secrecy and their effects on decisions about the solid rocket booster joints were responsible for the decision to launch. She says the conclusion of the Rogers Commission was that it was something like management arrogance in overriding engineering judgment. Vaughn believed that too when she started her research, but she concludes that no, it was not that, it was conformity that was the problem. The organizational culture and bureaucratic structure and political considerations. And so we're going back to the teleconference and we're drilling now in more depth now. The teleconference had 34 participants over 3 different sites at Kennedy Space Center, at Marshall Space Center in Alabama, and at Morton Thiokol in Wasatch, Utah. STS Mission 51L is what we're considering here. The level 4 levels, flight readiness review for 51L was on December 11th of 1985. Thiokol engineers reported that the solid rocket boosters were an acceptable risk in the manner that we just described and recommended launch. No information about the past performance of the joints was included because NASA's Delta reporting concept required contractors to report only on new evidence since the previous flight. And solid rocket boosters were already judged to be an acceptable risk, having gone through that rigorous process. On January 3rd, Larry Malloy's Level 3 flight readiness review at Marshall certified that solid rocket boosters were flight ready. Challenger's launch date had slipped because of 7 launch delays for the December launch of Columbia. Columbia launched on January 12th. This was a NASA record for false starts. This is serious because the whole rationale for the shuttle program was to have a recoverable space vehicle that could take payloads up and then return far more cheaply than you could do by shooting up a rocket that you lose entirely. But of course, in other words, the shuttle program was to make the space program, as it stood at the time, commercially viable, the manned space program commercially viable, because you're going to be taking commercial payloads that are helping to pay for the project. This is an acceptance of considerably more risk than we had otherwise in the space program. Prior to the shuttle program, the manned space program was entirely a scientific project. And of course, when you're doing science out of ignorance. You don't know what's going to happen. And therefore, you acknowledge that risk is most serious, and protection of human life is the most serious consideration. That's very expensive, as you know. So the shuttle program was to make space flight more commercially viable, but also more risky. I remember back in the early days of the shuttle program, listening to a NPR science writer discussing the shuttle program, saying that this was exactly the case, so that they were accepting more risk, and that ultimately at some point it was quite possible that you would lose the shuttle. No one had any idea what was going to happen as soon as it actually did. On January 13th, the Marshall Center Board Flight Readiness Review for the Challenger mission met. The major portion of Malloy's presentation concerned the parachute recovery again of the solid rocket boosters, which, rather than the joints, had been the most troublesome item for the solid rocket booster project during 1985. Since April of 85, the joints had been operating as expected. That included erosion of the O-rings, black and grease, but that became, and it no longer was anomalous because they expected to see it, and they did. The O-rings never burned more than a third of a radius through. Solid rocket boosters were certified in writing at level 3 and 2 flight readiness reviews on January 15th. On January 27th, Marshall's Larry Ware, the solid rocket motor manager, asked Thiokol and Wasatch to have its engineers review the possible effects of low temperature on the performance of the solid rocket motor. Temperatures on January 28th were expected to be in the low 20s in the early morning hours. In response, Robert Ebeling, ignition system manager at Thiokol, convened a meeting. The engineers expressed their concern about sealing at such low temperatures at ignition. After the January 27th scrub, Marshall and contractor representatives for the main engine, external tank, and solid rocket boosters were advised of the predicted low temperatures for January 28th and were polled by Stanley Reinhartz, manager of the Marshall Shuttle Project office, as to the feasibility of launch. All reported that there were no solid rocket booster constraints for launch at 9:38 a.m. Where, though, recalling Thiokol's concerns from January of 85, mentioned them. Robert Lund and Joe Kilminster agree that NASA should be contacted. So we get a three-way teleconference scheduled for 5:45 Eastern Standard Time. Thiokol takes no position at this point, either way. Another telecon is scheduled for 8:15. Prior to the 5:45 telecon, engineers at all three locations go to their data. At Thiokol, no field joint erosion had occurred since the flight of 51C in January of 85. That's the one that Beaujolais had inspected. The engineers had thought that the field joint problems were resolved. But now the projected low temperature raised the old questions. The question was a matter of joint dynamics, ignition pressure, and timing, as it had always been, but now the cold complicated things. Collectively, they decided they would need 13 charts. Lund divided up the responsibility for the charts at 5:30. Gerald Mason, senior vice president at Thiokol, and Calvin Wiggins, vice president and general manager of the Space Division, arrived. They had been elsewhere, but showed up at this is the first time they showed up. Thiokol would have recommended against launch. Those present, this would include Mason and Wiggins, decided that Thiokol would not recommend launch below 53 degrees. They admitted among themselves that they didn't have a very strong technical position. Phil Macbeth in particular felt that their position had been undermined by Beaujolais' admission that he hadn't remembered evidence of blow-by on flight 61A, which occurred at 75 degrees. But there was. So that suggests that the blow-by was not a function of temperature if it occurred at 75 degrees. The full group had not discussed that flight, having concentrated on flights at lower temperatures, since that was a concern. During Beaujolais' presentation, someone in Marshall pointed out the contradiction in Thiokol's data, blow-by also occurring in a flight at 75 degrees, indicating that temperature was not as a discriminator. It's at that point that Beaujolais was asked to quantify his concerns. After that, there was a neutral engineering exchange. The last chart provided by Thiokol was a temperature chart showing the contrasting 75 and 53 degree O-ring temperatures of the two flights with blow-by. Lund presented the engineering recommendation not to fly below 53 degrees, the O-ring temperature. Malloy from NASA asks Thiokol management for their recommendation. Kilminster replies he would not recommend, contrary to the engineering position. We've been through this. Malloy exclaims, this is before they go offline, "My God, Thiokol, when do you want me to launch? Next April?" George Hardy responds when asked that he was appalled at the Thiokol recommendation. Reinhartz asks Kilminster his comments. There's lots of pressure. Kilminster requests then the 5-minute offline caucus. NASA concluded that the data were inconclusive. Al McDonald, he's a Thiokol manager, admitted that they were. Thiokol's recommendation for 53 degrees as the baseline temperature. Oh, and incidentally, McDonald was the only one of the managers, Thiokol managers, who refused to sign off on the launch recommendation. Thiokol's recommendation for 53 degrees as the baseline temperature for decision-making was central to the controversy. In response to Mason, so they go offline. In response to Mason, Beaujolais and Thompson said that they didn't know what the secondary O-ring would do, that 51C, which they put it was the coolest motor Thiokol had ever fired. It had the most blow-by. that launch at the predicted temperature would be outside their experienced base of 53 degrees by 24 to 25 degrees Fahrenheit. Even at 40 degrees Fahrenheit, as temperature floor was too far out of the database in an area of known vulnerability. Mason replied that they all knew the seal was vulnerable to erosion, but it could tolerate it. Beaujolais responds that he couldn't quantify it, but in launching outside of the database, they were moving away from what he calls goodness. Mason asked them to recall McDonald's comment that if the primary failed, the secondary would be in position and would seal. Beaujolais and Thompson stressed that the resiliency tests provided the most important data. Mason responds that those tests did not incorporate pressure that acted on the O-ring during ignition. When tested with pressure, the O-ring acted as it was designed to operate, even in 30-degree tests. Mason asked if anyone has anything new, and that they were just going over the same ground at that point. Kilminster explained Mason's call for a management decision as typical when engineering disagreements couldn't be resolved by data that pulled toward consensus. Thompson and Beaujolais and other engineers believed that they'd done everything they could argue against the launch. But the information exchange that night, says Vaughn, was undermined by organizational strictures. The imperatives of the technical culture, bureaucratic accountability, and political accountability interfered with the production and exchange of information, essential to the hazard assessment. The engineers failed to make their case because their engineering argument deviated from the rigorous scientific standards of the original technical culture for flight readiness review risk assessments that the Wernher von Braun that he originated in NASA. On the other hand, their verbal opposition was impaired by bureaucratic and political accountability. Thiokol engineers themselves acknowledged that their position wasn't adequately supported by their data. When Marshall challenged Thiokol to prove it by quantifying their concerns, they were asking Thiokol to conform to standards of the technical culture by supplying quantitative data. When Beaujolais replied, I couldn't quantify it. I had no data to quantify it, but I did say I knew it was away from goodness in the current database. His reference to away from goodness in the database was known as an emotional argument. Real technology conformed to the norms of quantitative scientific positivism. Any flight readiness review engineering analysis that did not meet those standards was in effect a weak signal in the NASA system. In every flight readiness review, contractor engineers had to prove that their data supported their conclusions and their launch recommendations, whatever the recommendation was. Thiokol engineers believed that the burden of proof had shifted because they had never had to support a no-launch decision before. The truth is that the managers, that is, those who argued that the burden did not shift, were acting the way they had before. Now, NASA's, the idea of burden of proof here, which comes out of medieval logic and the law, in the law, burden of proof, say in a criminal trial, works so that it's the prosecution that has the burden of proof. Innocent until proven guilty. Prosecution has to prove their case. That's more important. You're not guilty unless prosecution has proved it. The standard assumption in all of this was the burden of proof rested with those who would recommend launch. That's the significance of what happened here, because for the first time, Thiokol is recommending against launching. So how does the burden of proof work here? This becomes very important for us. So, as according to Vaughn, again, Thiokol engineers believe the burden had shifted because they never had to support a no-launch decision before. That's true. But she says the truth is the managers were acting as they had before. The protocol, we have to separate NASA's position on burden of proof. The burden of proof rests with those recommending launch, which is what Thiokol had always had in every other contractor to NASA, including Johnson Controls and any number of contractors. had to prove that they were ready to launch. That was law practically. But at the same time, the flight readiness review protocols were such that NASA requires their contractors to prove everything. Every claim they make had to be proved, backed by data with this scientific paradigm. The managers were acting the way they had before that. The burden of proof shifted because the contractor's position had shifted to recommending against launch. There wasn't then a difference in procedures for launch and no launch recommendations. The same adversarial strategies and the tests of validity were required for both. Marshall's Ben Powers, who opposed the launch, corrected a Rogers Commission investigator's question. Mr. Molesworth, he's commissioner. Was it not an unusual position for a contractor to be in to prove that a system would not function? Ben Powers, I don't think you can use those words to prove that it would fail. I think he was put in a position to where he had to explain, and I'm not defending Hardy nor myself nor anybody else. I'm trying to be as accurate as I can. I think that your words should be chosen to say Thiokol was being put in a position to explain why their rationale was no fly. All right, so that's Vaughan. Let's finish by considering a little further this notion of burden of proof. Here's a piece of the Rogers Commission testimony. This is between Chairman Rogers himself and Robert Lund, the Vice President of Engineering at Thiokol. Rogers, how do you explain the fact that you seem to change your mind when you change your hat? Lund, I guess we've got to go back a little further in conversations than that. We have dealt with Marshall for a long time and have always been in the position of defending our position to make sure that we were ready to fly. And I guess I didn't realize until after that meeting and after several days that we had absolutely changed our position from what we had before. But that evening, I guess I'd never had those kinds of things come from the people at Marshall, that we had to prove to them that we weren't ready. And so we got ourselves in the thought process that we were trying to find some way to prove to them it wouldn't work. And we were unable to do that. We couldn't prove absolutely that motor wouldn't work. Rogers, in other words, you honestly believed that you had a duty to prove that it would not work. Lund, well, that's kind of the mode we got ourselves into that evening. It seems like we've always been in the opposite mode. I should have detected that, but I did not. But the roles kind of switched. We'll come back to that. So that exchange is on one of the slides. Here's another one. Before we get to that, you also see a slide for what is a paradigmatic engineering decision and a paradigmatic management decision. Paradigmatic engineering decision is the decision that should be made by engineers or at least governed by professional engineering standards because it either, one, involves technical matters that require engineering expertise, or two, falls within the ethical standards embodied in engineering codes, especially those that require engineers to protect the health and safety of the public. So this comes from a text on engineering ethics by Harris, Pritchard, and Rabins, and they're using this in assessing what happened at Challenger. So what, in other words, what is the relationship between engineering and management? Understood in terms of decision-making authority. So they are saying that engineers ought to have the authority to make it, so management ought to defer to engineers, again, when either the decision involves technical expertise. The decision falls within their technical expertise. Or second, falls within the ethical standards embodied in their codes, especially those that require engineers to protect the health and safety of the public. So management then ought to defer to engineering when either of those conditions obtain. A paradigmatic management decision is a decision that should be made by managers, or at least governed by management considerations, because either one, it involves factors relating to the well-being of the organization, such as cost, scheduling, and marketing, and employee morale or welfare. And two, the decision does not force engineers or other professionals to make unacceptable compromises with their own technical or ethical standards. In other words, the PED operates as a set of constraints, as a brake on management decision making. Ordinarily, it's management that makes decisions, but in those either conditions 1 or 2 of the PED or condition 2 of the PMD, if those obtain, management ought to defer to engineering. Here's another portion of testimony. This is between Commissioner Dr. Keel and Jerry Mason, the general manager at Morton Thiokol. Dr. Keel, since Mr. Lund was your vice president of engineering, and since he presented the charts and the recommendations not to launch outside of your experience base, that is below a temperature of 53 degrees for the O-rings, in the previous 8:45 Eastern Standard Time teleconference, what did you have in mind when you told him to take off his engineering hat and put on his management hat? Mr. Mason, I had in mind the fact that we had identified that we could not quantify the movement of that, the time for movement of the primary O-ring. We didn't have the data to do that, and therefore it was going to take a judgment rather than a precise engineering calculation in order to conclude what we needed to conclude. And then we recall what the exchange was between Mason and Beaujolais Thompson. Now, Harris, Pritchard, and Ravens in their engineering ethics text say that Mason could be taken to argue that the decision to recommend launching did not violate provision 2 of the PMD, that is, that you're asking engineers to violate their ethical standards or technical standards, and also that the decision did not clearly satisfy provision 1 of the PED. But they say, given the gravity of the situation, that the Challenger would be destroyed if the O-rings failed, surely engineering consideration should take precedence over management ones. Still, they say, the engineers were not comfortable with the absence of data for the performance of the O-rings at low temperatures. This is borne out both in the absence of engineering contributions to the teleconference itself before the launch and in Vaughn's interviews later on. Mason, being an engineer himself, certainly would have known this. Nonetheless, provision 2 of the PED was relevant because the decision to recommend launching violates engineers' propensity to modify or change criteria only in small increments. Launch temperature was expected to be more than 20 degrees lower than that for any previous launch. This was an enormous change, which should have given an engineer a good reason to object to the launch. Moreover, provision 1 of the PED was relevant, even though the data were limited and clearly did not give conclusive evidence that there would be a disaster. The data seemed to point in that direction. Engineers also know that composites such as the Viton material of which the O-rings were made are temperature sensitive. One could reasonably expect substantially lower temperatures to produce substantially more blow-by problems. Finally, provision 2 of the PED was relevant because life was at stake. Practically all engineering codes of ethics give paramount importance to life and safety. The failure of the O-rings would be catastrophic. All right, so what happened? The Rogers Commission concluded that NASA and Thiokol management arrogantly overrode engineering judgment. This is what we said Diane Vaughan also believed at the beginning of her study. She concluded, however, that it was the technical culture of scientific positivism and bureaucratic and political accountability. In other words, organizational dynamics, in other words, conformity, that were responsible. That's a sociological explanation. Being concerned with ethics, though, we can draw a separate, although maybe compatible, conclusion. Recall at this point the Rogers and Lund exchange. Of that exchange, Harris, Pritchard, and Rabin say this last-minute reversal of a long-standing policy requiring the burden of proof to rest with anyone recommending a no launch rather than a launch decision was a serious threat to the integrity of the engineering obligation to protect human life. They say further, if the person making the recommendation wore both an engineering hat and a management hat, as Robert Lund did, he should have kept his engineering hat on when he made the decision. All right, now, metaphors such as hat switching are often useful, but they also can be misleading. What Harris, Pritchard, and Rabin says comports with what the Rogers Commission concluded. But let's look at Lund's testimony again. He says he should have noticed the switch in the burden of proof, but failed to. Using the metaphor of hat switching, Harris, Pritchard, and Rabin assume that the problem was a conscious decision to comply with the PMD over the PED. It wasn't. That is, to have his management hat on over his engineering hat. It wasn't, though. Lund, along with practically everyone else, failed to notice the switch in the burden of proof, providing a sociological explanation for what happened. It's not as simple. That is, conditions under which engineers and other, as we'll call them later on, bureaucratic professionals work, repress their professional judgment. That autonomy is what all professionals demand in their work, that they be able to use their judgment as they see fit. But the conditions under which bureaucratic, that is, professionals who are employed, work, repress that judgment, make their autonomy less effective, make them less autonomous. That's a problem. That's our concern, if not Vaughn's. Hence, moral friendship is a professional's response to anticipated possible regret. Now, today I I put links in Blackboard to 3 different NPR short reports on the Challenger. 2 on Robert Ebeling, the ignition manager at Thiokol, who grieved for 30 years every day that he didn't do more. Turns out he was the only engineer who actually thought that the shuttle would be lost, would blow up on the launch pad, actually. Moral friendship is designed as the professional's response to anticipated possible regret. So if we understand that this is a condition of one's work, that one's autonomy is constrained or limited or repressed by your working conditions, that's embarrassing. There should be something that we can do about that. I said that Lund and practically everyone else in the teleconference failed to notice the switch in the burden of proof. Beaujolais, at his Marquette talk in 2003, after his talk, told me that there was one person who did notice this, a junior engineer who was there, Thiokol engineer, mainly to observe. He'd had the distance necessary to see what was happening. That tells us it's possible to have that distance, and it's the purpose of moral friendship to cultivate it. All right, so the most important thing in all of this is this notion of burden of proof. One of the slides, which one it is, summarizes what's going on with it. Slide 16. So ordinarily for engineers in this sort of situation, the burden of proof, remember we said that in NASA, the standard assumption was the burden of proof rests with those who would recommend launch. But let's generalize a bit more. In this sort of situation that engineers would be in, the burden of proof would be on them to prove that X, whatever X is safe. And that is that there's an acceptable risk. In this case, it's the O-rings. So that's the standard burden. The night before the launch, they were asked to prove that X would fail, which obviously is a considerably higher standard of proof than otherwise, and something that engineers shouldn't have to do. That's not their task. That is what Lund says he failed to detect, that switch. Harris, Pritchard, and Rabens don't make any much of that, but that is extremely important for us. If we begin with understanding ethics as an answer to the question, what ought I to do? It assumes that an ethical problem is one that where the question arises. If the question doesn't arise, you don't have an ethical problem. This whole episode betrays that. If you listen to the Ebeling NPR pieces on Robert Ebeling, one is 30 years after the launch, January of last year, maybe a couple of years ago. And then 2 months later, Ebeling had died 2 months later. And so they do an obituary piece on him and what had happened since the first NPR broadcast about this. But the point is that he tortured himself for 30 years about that. That tells us, that regret tells us that this was something ethically important that happened. He regretted not having noticed it. And that's what moral friendship is designed to address.